Hello, geometers. I am here to talk to you about a topic in geometry called transformations. And it's actually a whole branch of geometry. You can actually take college classes as a math major on just transformational geometry. So basically, we're dealing with transformers, right? Wrong. Instead, we're dealing with transformations as something that moves a figure. So let's go ahead and move this guy out of the picture and talk about some transformations. Now, there are four basic transformations, and as you can see here, I have 1, 2, 3. Well, that's because these are sort of special in that they have something in common that the fourth one does not have. So let's talk about these real quickly. A reflection is like a mirror image. A translation, sometimes we call a slide or a glide. It's basically just sliding something around. And a rotation is turning it. It might be turning it around a different point, or it might be just turning it around on top of itself, like right where it's sitting already. Now, what these three have in common is that they all do something called preserving size. Okay, now preserve means to keep the same. Okay, so all three of these preserve the size of the figure. And what's special about that is that makes them a special group of transformations that we call either rigid transformations. Can't. And let me go grab my text tool that I thought I had. Rigid transformations. The word rigid basically is the opposite of the word flexible. So in other words, this is something that does not change at all. Rigid, the shape stays exactly the same. And that means the size stays exactly the same. And the other term for that is isometry. If you are taking biology or have taken biology, you might notice that there are two root words in there. Iso means same, and metra, or metri in this case, basically means measure. So same measure. So these are three different ways of saying the same thing about this set of transformations. These three transformations, reflections, translations, and rotations, are all called isometries or rigid transformations because they preserve the size and therefore really also the shape of the figure. Now, there are really four transformations. I mentioned that earlier, that this is not all the transformations there are, but the last one is sort of in a set by itself when we talk about these particular characteristics. So the fourth one is dilations. And I went ahead and put it underneath a little dotted line there to just sort of separate it from the rest, because a dilation is basically an enlargement or a reduction, which is changing the size. Okay, so it does not preserve size. So these up here all preserve size. We can call them either rigid transformations or isometries. Those two terms are used kind of interchangeably. They really mean the same thing. But dilations do not preserve size. You can see right there, this particular little treble clef gets bigger and becomes this one. So an enlargement or reduction is a dilation. So the next thing I want to talk to you about is some of the characteristics of each of these. There are specific characteristics that we need to know about to be able to perform reflections or translations or rotations and to talk about them. Okay, so the first one we're going to talk about right now is reflections. And if I'm asking you to do a reflection, you basically have to know where is the mirror. What am I reflecting off of or over, really? So we are going to grab a line. Anytime you have a reflection, you have to reflect across a line. And in this case, I have a dotted line. It doesn't have to be dotted. It can be solid. So let's go ahead and make it a solid line. So I have to know which line I'm reflecting across. Okay, so you can't ask somebody to do a reflection without telling them what line to reflect over. And it's always over a line. It's never reflecting over a point or anything like that. So first thing is I'm going to mark this as my mirror. That tells it that this is the line you're reflecting over. And then I'm going to take that figure and I'm going to say, let's reflect it over that. And it looks like this. Now, this is a program called Geometry Sketchpad, and I like to use this because when it does it in the right way. It's not just drawing it where it thinks it should go. It's actually performing a reflection so that if I move the line or if I move the figure in any way, it still works out right. It's still a reflection. One of the things that I just kind of showed you that I want to point out to you is if you take a point that is on the line of reflection itself and reflect it, well, then the new point is also on the line of reflection. Now, in general, this is not just a reflection thing, but in general, for all transformations, we like to call the original the pre-image. So this over here would be my pre-image, and the result is called the image, which kind of makes sense because if you think about a mirror, if you go walk into the bathroom and you look in the mirror, you are looking at your image. Your image is the result. The pre-image is what was there before you looked in the mirror. You were already there. So you are the pre-image in that case, and your image is the result of the reflection. So I really like these because you can play around with it and you'll see that it looks like a reflection no matter what and no matter where I put this line. I could even put it up here. There we go. All right, so let's look at a little bit more generic shape. So I'm going to look at, hang on, let me grab it. I'm going to look at a segment, a couple segments attached to each other here. And I want to reflect those, and in reflecting those across my line, I'm going to make that line. I want to show you some characteristics of reflections. So we already know that we have to know what line we're reflecting across. And we mark that. And excuse my computer going ding. And I reflect, and there we go. Now, one thing I want to show you is I want to show you the points of the image. Remember, image is result. Pre-image is what it was to begin with. And I'm going to show the labels of those. And this is one of the ways that sometimes, not always, but sometimes we label the points of our image with a little apostrophe that basically tells me this is the first result after I have done a reflection or a rotation or anything, any kind of geometric transformation. The way we read these as A prime, B prime, and C prime. Okay, so let's look at certain characteristics here. First thing I want you to notice is that if I were to connect each point and its image point, every single point and its image point, then what I have is I have segments, all three of these segments that are, I'm going to make them dotted to make them a little bit less obvious. All three of those dotted segments are perpendicular to the line of reflection, meaning 90 degrees. They all make a 90-degree angle here where they meet the line of reflection. And that's true no matter what. No matter what do I do to that line, when a point moves across the line of reflection, it moves in such a way that its path, see the path between A and A prime, is perpendicular, is 90 degrees with this line of reflection. So the dotted line makes a 90-degree angle with the pink line. And that's the truth for every single one of those dotted lines anytime you have a reflection. Another thing to know about that is the line of reflection is the midpoint of that path. I'm going to construct the midpoint and you will see that. Now another thing that tells me, oops, I've got too much highlighted. Another way of saying the exact same thing, that the line of reflection crosses that dotted line right in the middle. Another way of saying that is that from here to here, that distance, and they called that point H, is the same as from C prime. From C to H and from C prime to H is the same distance. Okay, now that's actually very important. What it tells me is that if I reflect a point across a line, in this case my point would be C. C is originally 6.54 centimeters from the line. The new C, C prime, is also 6.54 centimeters from the line. So when you reflect a point across a line, however far it was from the line to begin with, it's going to stay that same distance away from the line. However far this is from A to the line, same distance from A prime to the line. A to the line is 1.13 centimeters, and A prime to the line also 1.13 centimeters. That's always true for a reflection. It stays the same distance away from the line, it just flips over onto the other side. Okay? So again, it moves in a path that is perpendicular to the line of reflection, and it will always be the same distance away from the line of reflection, just on the other side. Last thing I want to show you with reflections, and I didn't quite clean up everything there, is I want to take this rectangle and I want to reflect it over a line. Okay, and what I want you to see is that one of the things that changes when you are doing a reflection is something called the orientation. The orientation of a figure is basically like saying which way it's pointing. Now, obviously a rectangle doesn't really point, but you can see it with this rectangle because you can see, let's move this. I'm going to move this line. If I were to put this line of reflection right in between these two figures and reflect it across there, you can see that G used to be on the right-hand side of the figure, and now it's on the left-hand side of the figure. E used to be on the left-hand side of the figure, now it's on the right-hand side of the figure. The points aren't in the same order over here as they were over there. So another way of thinking about that is like if we have a little shape, and let's say we have a shape, I'm going to get rid of that. When we make a shape, when we say which way it's pointing, let's go ahead and make a shape that's kind of like an arrow. If I have an arrow that is pointing to the left, and I'm going to go ahead and fill this in just for fun. So I have an arrow that is yellow that is pointing to the left. If I reflect it over my line, it's not going to be pointing to the left anymore. It's going to be pointing to the right. Correct. Okay, so even when the shape doesn't look different, the points are no longer in the same positions. So that means the orientation has changed, the way something is facing. So let's just go through those real quick. Facts about reflections. A point and its pre-image, or let's say a point and its image, are the same distance away from the line of reflection. Okay, and that's actually the second thing I want to say, because the first thing I want to say is that there always has to be a line of reflection. So let's go ahead and put that in. So the first thing I need to know is what line am I reflecting my figure across. The second thing I need to know is that every point and its image, in other words, where it goes, are going to be the same distance away from the line of reflection, like D and D prime are the same distance away from the line of reflection. They're farther away, so it's going to stay farther away. F is close to the line of reflection, so F prime is also going to be close to the line of reflection. Our next fact about reflections is the line of reflection bisects the segment between a point and its image. In other words, bisect means cuts into two equal pieces. So if I pick a point on my arrow over here and a point on my arrow over here, and I connect those, then this dotted line cuts that into two equal parts. And I need to add to that, and actually, let me just go ahead and say the line of reflection is the perpendicular bisector. Let's put it that way, because that's the other thing. It makes a 90-degree angle. It is the perpendicular bisector. It's perpendicular. It's a 90-degree angle, perpendicular bisector of the segment between a point and its image. And then the last thing we need to know about reflections is that orientation is not preserved. it's not going to be still pointing the same way it was to begin with. So these are sort of our 4 facts we need to know about reflections. So let's look at translations. A translation takes a shape. In this case, I've got this little crown looking thing, and it basically just slides it. So I'm going to tell this to translate it, and I can tell it how far and in what direction. Notice you always have to tell those 2 things, how far and what direction. This particular thing is giving me angles and distance as a way of saying that. So I could say like negative 70 degrees, or I could say 100 degrees, and it's going to go in different directions with that. 180 degrees, I'm going to say 0 degrees. And let's say I want to move it 7 centimeters. Well, then it's moving that way. Let's make it 70 degrees. Well, it's up there. You can almost not see it. How about negative 90 degrees? Goes down. So that's one way to tell you how far and what distance. Another way is by saying how far to the left and right and how far up and down. So that's horizontal and vertical. This is saying I want to go 7 horizontal, which means to the right, and I went 1 up. I could make it go 7 right and 3 up, or I could make it go 7 right and 5 down. Now let's talk about the other characteristics we talked about for reflections. Okay, so on this one, I went ahead and sort of shaded the image. This is the image. Remember, that's where we started, so that's the pre-image. But the other way you can tell what's the image and what's the pre-image is, remember these little apostrophes. This is I prime, K prime, L prime. If we were to translate it again, or it doesn't have to be a translation, it could be any kind of transformation, then those points now will have 2 little apostrophes, and the way we'll say that is double prime. See the K double prime, L double prime, and so on. So that's how we say that, but we don't really need to see that. The first thing I want you to notice here is that the orientation does not change. It doesn't point in a different way. Think about this little part with the I as being sort of like a pointer, like a finger pointing up. It's still pointing up in the exact same direction it was before. The L is still on the right-hand side of the figure. The K is still on the top of the figure. The H is still on the bottom of the figure. The way it's positioned, its orientation has not changed at all. The way we say that is that orientation is preserved. It stays the same. Remember, for reflections, it was not preserved. And for both of them, the size is preserved. The size has not changed at all. The next thing I want for you to notice about this is when I move from K to K prime, or from L to L prime, when I move from any point to its image, each of those paths is going to be parallel to each other. From L to L prime, whoops, I have too many things highlighted, from L to L prime, or from H to H prime. I'm always moving in such a way that all those paths are parallel. Change my figure, and they still will be. Okay, so that's just sort of a fun fact, but let's go back to another thing I want to type here that we mentioned already, and that is that the 2 things we need to know in order to do a translation are how far and which direction. It's kind of like if I told you, I pointed at a box and I said, slide that box across the floor. You might say, well, which way do you want me to slide it? Where do you want me to slide it? How far do you want me to slide it? When do you want me to stop? That's what we have to be able to tell for a translation. And finally, the last of the 3 isometries, or rigid transformations, meaning the ones that keep the size the same, is the rotation. And I want to just look first at what do we need to know to rotate something. So there is more to know about this than either of the other 2. We need to know how far. We need to know in which direction. And in this case, when we're turning something, that generally means clockwise or counterclockwise. Sometimes we use the CW for clockwise and CCW for counterclockwise. And then last but not least, we need to know around which center, because you can rotate things around different points. I could rotate this point or this figure around a point that is on the figure. I could rotate it. Let me move it so you can see a little better. I could pick this point and I could say I'm going to spin it around that point. And I can rotate everything else here. Do a better job of grabbing it. Right around that one point here on the corner. I can rotate it 90 degrees or 100 degrees, and to go the other way I have to make it negative. We won't be using that usually. That's just the way this program works. I can rotate it different ways. Now that's all rotating around this one point right here. I could also rotate it around a point that is not part of the figure. I could rotate it around this point over here. So I'm going to mark that as my center, and then I'm going to take the whole figure and I'm going to rotate it around that point. And I could rotate it however far I want to. And this is just different ways of telling it how far I want to go. Notice that this is going counterclockwise, standard, and clockwise would be the other way. Counterclockwise means like this. Let me draw like this. If you are not told, sometimes they will not tell you which direction. If you're not told which direction, we assume counterclockwise. Okay? You are usually told, but if you're not told, you assume it means counterclockwise. And that's the main stuff you need to know about a rotation, really. Some other fun facts. Now, remember, it's an isometry, so not only does that mean that every point on here, let's go ahead and rotate it. Uh-oh. Hang on. Okay, so the fact that it's an isometry, which tells me preserving size, not only tells me like that this segment is exactly the same as this segment length, but it also tells me that every point, let's say this point, and its image, whoops, I didn't mean to do that. Okay, so I had to hand label this guy, but every point and its image, let's see if I can get that to get a little smaller. There we go. This point right here, if this is J, then this is J prime right over here. They would both be the same distance away from the center. It's trying to give me another thing, but this distance here, this distance here. So not only are they the same, all of the size things are the same, everything about size. Not only the length of the segment, not only how far points are apart from each other, but also how far everything is from the center of rotation in this case. And that is pretty much your overview of everything you need to know about the three isometries. Oh, I left out one last thing. Notice the orientation has not stayed the same. Okay, this is not pointing the same way this was pointing. All right, so the orientation is not preserved. The only one of our three isometries that preserves orientation is a translation. Everything else, the way the figure is sitting changes. It either flips over or it turns. Okay? So there you have it. Pretty much everything you need to know about the basics of reflections, translations, and rotations. Those are the three transformations that are all isometries or rigid transformations because they preserve size. They keep the size the same, which means that the new figure and the old figure are congruent. Thank you for joining me, and I'll see you next time.